Okay, so we have today Daniele from Swiss Lab, IDSIA at Università della Svizzera Italiana in Lugano in Switzerland. And he has a PhD degree also from USI and did a thesis on anomaly detection and change detection in sequences of graph. He has a Master of Science and a Bachelor of Science in Mathematics from Università degli Studi di Milano. My Italian is not so great, in Milan. And he was a visiting researcher and an intern at different places in University of Florida, University of Exeter, at ST Microelectronics in Geneva. And he's interested in different things: machine learning on graph structured data, time series analysis, and learning in non-stationary environments. Yeah, so he has publications in different various renowned conferences and journals like ICML, NeurIPS. Yeah, and I think that's it. So yeah, let me know if I missed something.
No, the pronunciation was pretty perfect. Okay, so yes, this is me. I'm Daniele. This is a work that I carried out with Cesare Alippi. It's about Kalman filters and graph data. So do you see also my pointer? Okay, great. So I will start with a bit of context. So this paper combines two elements. One is state space modeling, and the other part is regarding more the Kalman refinement and filtering. So what's a graph state space model? Well, let's make a bit step back. So our generic state space model is a model where which is driven by a certain input, here represented by X. And this input is fed to a system that has a state. Let's say time t-1 is this h here in blue. And combining the input with the current state, we have a state transition to a new state h. And this state transition can be affected also by some noise term. Okay, after the system changes states, it can emit some output. Okay, could be what we actually observed from the system. Typically the states are hidden, the input are either provided by us or we have access to it, but the states are hidden, and the outputs is what we observe only at late time, and we want to typically predict. So we try to model the system to make our prediction of the Y. Okay, so this is typically done where input states and outputs are vector data. In this work, we move a bit further and we consider, instead of vectors, graphs. Okay, so inputs, states, and outputs can be graphs. Okay, what it means to combine all of this, we will see this throughout the presentation, but this is the high level of idea of a graph state space model. So what's important is typically that we may know the topology here, we may know the topology of the output, but we don't typically have the topology of the states. Okay, this is z to the -1, if you're not familiar, just represents the fact that here we have a step t, and we move one step back in time, so we have a step t-1. Okay, regarding instead the Kalman filter part, I don't know how much you're familiar, but anyways, so typically, not typically, we always have a system model. So a model that is the actual environment that generates our data. So we suppose it behaves in this manner. So we have a state, and the output is only given by the current state of the system plus possibly some noise, and also maybe the transition is affected by noise, as we have seen. Okay, so this is a system model. It's something that we want to model, but we don't have access to except for the outputs and the inputs. Then what we have is our predictive model, right? So the model that has some parameters here represented by theta and psi, which are the parameters that we learn in order to better, at our best, fit the data that we have, okay? This could be, for example, in our case, a spatial temporal graph neural network. So when we need to make our predictions, so here we see the hat symbol to represent the fact that these are our estimates of the states. Need not to be exactly the states because we don't have access to it, but we make some approximation or estimates of that. So we take our estimates, we iterate through this process like it was a standard recurrent neural networks area network, and we make our prediction Y. So the Kalman filter part enters in this process here by improving over the estimates of the state. And very briefly, it works as follows. So after we have fed our input to the system and we have our previous estimate, we make our transition, for example, using the model that we have learned, we obtain this state estimates, let's say, and we make our prediction y of t. Okay. After some times, it's not rare that we have that we observe the real target, the real output of the system model, so this model over here, and by means of these two, comparing these two, we can improve over our estimate h of t, here represented by a minus. When refined, I will use the notation plus. So it is refined and then fed back to the state transition, okay? Over time, we will see a bit more later, over time, this will improve our estimate of the current state in order to make better predictions, okay? So this was very quick overview of graph statistics models and Kalman filters. So Kalman filters defines how this refinement process is carried out. So to derive it, I will not derive fully it, but just to show you how it is constructed, let's assume we have a linear system. So, okay, this is our system model, and we have the state transition function or operation that is linear in both the states and also the inputs. So all the entities involved here are vector at this point, and we have again also a linear readout function. Okay, this process we assume iterates over time and spits out our data that we collect. So let's say that we are considering the squared error, so the Euclidean distance between the true output of the system and our predictions. Then we know that the optimal predictor, if we get to know the F, G, and H operators, is exactly the system model by neglecting of the noise terms. The noise terms, I haven't said it, but we assume it to be white noise. It means that they are uncorrelated between each other and also are zero mean. So we expect to fluctuate around 0. So this is a theoretical result that tells us that the optimal squared error is achieved by this predictor here. So a thing that I want to point out here is that this, different from what we have seen before, is a time variant system. What does it mean, time variant? It means that the transition functions and the readout can depend on time. So over time, it can change. This is not what we are going to tackle in the end, but is necessary for us in order to derive a Kalman filter refinement that operates also for our nonlinear systems. So this is somehow propedeutical. So as I said, we are going to distinguish between a priori estimates, so before the refinement, and a posteriori estimates, okay? So here it's our optimal predictor, and the Kalman filter integrates or updates the state using target the true output whenever it comes available. It doesn't need to be always available, but whenever we have access to it, we can use it to integrate. Of course, we don't use this to make our prediction. We only observe it typically after we made our prediction. But still, this reflects back on the next state estimates that hopefully will be beneficial to the next prediction. Okay, so this is the nomenclature that I will use. So a priori state estimate means that it's a state estimated before the refinement, and a posteriori after the refinement. Also, the color coding should remain the same throughout the presentation. So green is the input, blue is the state, this is a posteriori, and this is the target. So I won't discuss it too much on this, but another important aspect is that not only we have an estimate of the states, but we can also carry over with our operations also what is typically called error covariance matrix, or matrices, because there are two actually. So these matrices here are the variance of this vector here. So basically the discrepancy between our estimates and the true state, which is unknown, ungiven to us. Okay, so this is how it is defined. Of course, over time, we would have an estimate of this matrix here. Similarly, we have this a posteriori error covariant matrix here. Okay, so these two are refined in a very similar process, but I will omit it just for clarity of the presentation. So again, if anything is unclear, please stop me anytime, because this is a bit important, that concept that we need to rely on later on. So our prediction is, again, as I said, we have our state estimate of the previous time, we make a new state estimate, and we make our prediction based on that state estimate. Then, as soon as we observed this, what we can do is make our refinement. The Kalman refinement is pretty simple in formula, because it's a displacement with respect to the previous state, which is to which we add a matrix. Well, this innovation, which is the discrepancy, multiplied by a matrix. This matrix here is typically called gain, or Kalman gain, if it is derived according to the Kalman procedure, and allows us to improve over this. What's really interesting is that, so we have that the a priori state estimate, it's an unbiased estimator of this quantity here, okay? And it turns out that also the a posteriori state estimate is an unbiased estimator, regardless of the choice of k. Why it is so? Well, it is so because so the discrepancy here in expectation is always 0, because we have, well, we didn't prove it, but we know that this predictor here is the optimal predictor with respect to the squared error. Okay, so in this regards, regardless of the choice, we know that we won't access this unbiased property, that it's really desirable for our state. Okay, so, and secondly, this allows us to choose k in order to minimize the prediction error. So given that we have this estimate here, we can choose k so that the estimates, the refined estimates of the states, allows us to provide a better prediction of the target. Okay, so we select k so as to minimize this error here. Well, after some computations, it turns out that the optimal matrix k is given by this formula here. There are really so many formulas that can provide the best estimates that are reformulation in order to achieve these or that properties, to be numerical, more stable, and so on. But let's stick to this, which is not really important at this point, which one we use. But the point is that we can derive analytically which is the best gain that we can employ over here. And as you can see, we employ this h, which is associated with the readout. We have p, which is associated with the uncertainty that we had so far about the state estimates. And we have also the variance, or the covariance matrix of the noise term nu associated with the readout. Okay, so this is critical and impact, of course, our refinement of the state, of course. Okay, so this was Kalman for linear systems. And now we need to move forward, or we want to move forward to graph state space models. Before moving that much further, I will bother you a bit longer on graph state space models. So, so far we have considering a linear system. A first step beyond that is considering a nonlinear interaction between the states and the inputs, okay? But still we have additive noise. This is already a good system that does not involve so many complications, but another step further would be to include some noise that interacts non-linearly with the system. Take, for example, could be multiplicative noise or any other type of interaction that we can think of, and this creates further complications to our system. But at this point, all the entities involved here are vector data, okay, as exemplified here. What we need to model when dealing with graphs is what we call graph state space model that we're further discussed in this paper over here, is that inputs, states, and outputs can be graphs. So basically a bunch of nodes connected by edges, and potentially we can have also attributes associated with the nodes and the edges of each entity over here. Okay, so we have this state space model, which is analog to the previous one, just the entities are graphs. As far as noise are concerned, we have different modalities in which we can model noise affecting the graphs. Probably the most simple one, the simplest one could be having some noise that impact on the node signals, so the attributes that we have at every time step associated with each node. But also could be a perturbation of the topology of the states, for example. And this will, of course, impact further later on how we will instantiate our final Kalman gain. Okay. Okay, so this was a system model. Okay, we already have graphs in here, and we have also a predictive model, which is basically roughly the same, but it's encoded, it's represented here by theta, psi, and var theta as the parameters of our model. So the only change that you see here is just for clarity later on, which is that we have an additional block here, which we called input encoder, that takes the input, it passes through this block before feeding it to the state transition. All the rest pretty much is the same. We have this dice here that represents that the state transition could be probabilistic, okay? The state transition and also the readout, okay? And then we will see that we have this Kalman refinement once again. So what's important to remember is that here we have a system model and a predictive model. The predictive model typically will be a deep learning model, and we do not expect to have the states here that match one-to-one the states of the system model. This is also the case when we have a recurrent neural network, right? When we don't know the dimension of the states, we just set a sufficiently large state dimension, and then we operate with that. In fact, this is not unnecessarily a condition to have, so this system identification, so to match exactly the operation. What we need to model is that the data, the input and the output should be described in a similar manner. So in other terms, what this entails is that we may have a mapping that relates the state of the predictive model with the state of the system model, but doesn't need to be represented in the same way. Okay. This will occur also in some terms also in the experiment and the empirical part that I will show you at the end. The other aspect is that, well, actually I already mentioned it, is that the models are probabilistic here. So involves some learning of probability distributions associated with the state transition and the readout. And as you can imagine, having that the states are graphs, and these graphs are not given to us in most cases, entails learning a distribution over discrete entities. So here we see that we have inputs, states, and outputs. Input, states, and outputs are all graphs, and they are all based on node set and edge sets that need not to be the same throughout an entire process. So for example, here we have an example where the node sets are the same. So we have this identification between the nodes, the input, the state, and also the output. This could be the case where, I don't know, we are gonna learn some states associated with the nodes that we actually see. It's like a sensor network that you fully observe. And then we learn only the relational information associated with these sensors. Okay, another setup could be where we have input and output graphs, which are the same, except also for sure for the signals associated with the nodes, but the topology could be the same. And we learn a state representation that somehow could, let's say, simplify, or in the like in the example of a factor analysis, right? So here we have a few nodes that impact on only these nodes, and other nodes that impact on these, and then we need to map back this simplified or coordinate graph back to the original node sets that we have. Other scenarios are possible. Here we have an example where we have, for example, partial observability. So all nodes corresponds one-to-one, except for the red ones, which are simply not observed, but are there, and we try to model them, okay? Another type of relation that may or may not exist between the nodes of the graphs involved is associated with this temporal relation. I would say that the far majority of the scenarios involves this type of relation. So we know that this node at time t correspond exactly to these other nodes at time t+1. So if you imagine a sensor network, you can easily guess that the same sensor is recorded over time, and there is this matching that we can always reconstruct. Doesn't need to be that the topology doesn't change, or for a certain period of time where we may miss some nodes, but we can always tell that after some time this may correspond to this node or not, okay? So because of this difficulty associated with the relations of the nodes at different in the different spaces, right? The input, state, and output spaces. What we may need to employ is a graph pooling operator at a certain point of the processing, typically in the input encoder, where we try to map substantially the input graph or the nodes of the input graph to the nodes of the state graph that we have from the previous iteration. And for carrying out this operation, there is this framework called select, reduce, and connect that allows us to choose, among other things, the most appropriate pooling operator among all that have been proposed so far in order to meet the specific requirements that we have in the current scenarios. As you can imagine, there is no one-size-fits-all in these cases, because as we are moving to more and more complex objects, it's getting important to understand as much as we can what it's relevant for us. So this is a first way to encode such a structure. For example, from the previous slide, if we know there is such a correspondence, then maybe pooling operator is not helpful at all, so we can completely skip it. But if we know that should be something of this sort, then we may want to require it. Another aspect that we developed in our lab is regarding the learning of a topology associated with the states in this case. Okay, so our model is probabilistic, so is based on so within the state transition, we learn a probability distribution, here P of theta, associated with the adjacency matrix of the state, the graph state. This encodes only the uncertainty associated with the topology, and this could be conditioned, and typically it is conditioned on the previous state and the input that we have just fed to the system. Okay, this allows us to model a probabilistic topology while keeping the topology or the graph a discrete object, so keeping edges either present or not. Potentially, we can also add some weights to tell whether an edge is more strong than another, and so on. But we wanted to keep the entity discrete. Okay, and in order to do so, what we actually propose to use is score-based optimization techniques that allows us to optimize over this expectation. This is basically our loss, right? We have a loss that combines the predicted net target, and the predicted net target uses the topology, but this topology is a probabilistic entity, so we take the expectation overall, the possible outcomes according to this distribution, and we need to take the gradient, but the gradient is associated with this probability. So this creates some complications that we decided to approach from a score-based perspective that allows us to have many advantages, but I would like to redirect to the paper itself because it's a long story by itself. So, but the point is that at some point we can model, so our random variable associated with the topology as basically a structural part. So a sort of topology defined only by a parameter theta, and decouple the noise into a different term that allows us to distinguish between this structural part and treat the noise as a separate entity. So this was our predictive model that we considered here, but in general should be anything that has this form, a form like this. Okay. Okay, let's move on Kalman filters, but for graph state space models. So the Kalman filter I presented a few slides before was related to linear systems, actual linear time invariant systems, but linear systems. Now we are dealing with non-linear systems, and by the way, we also have graph structure data. So to develop a linear system, a Kalman filter for such a systems, what we propose to do as a first way to approach this problem is to consider what is called extended Kalman filter. So the extended Kalman filter has been designed the last around 1962 for dealing with nonlinear system for vector data. And at the core of the extended Kalman filter, there is the fact that we may have a nonlinear system like so, but when we reach a state, what we can do is approximate the system around this operating condition defined by this system state and the provided input. So we approximated it by linearizing the system around these operating conditions. So this is done, for example, by Taylor expansion. So Taylor expansion, as I'm sure you know, basically approximate these nonlinear functions around a point by considering the derivative, which allows us to define a linear mapping. Plus, there is, of course, an error that we can expand further, but here, for simplicity, we stop to the first one. So, for example, let's say that we are considering only this second part, so the readout, which is still a nonlinear function of both the state, the current state, or the current state estimates, depending on how we are using it, and the noise. What we can do is approximate it around any state and any realization of the noise by considering the Taylor expansion around this point here. So the current state estimates and the presence, the absence actually of noise, okay? Or the expected value with respect to all possible realizations of the noise. So then we need to take a gradient, so the derivative with respect to the first element or the first variable of this function, and then the derivative with respect to the second variable or argument of the function. And then we have this displacement here, okay, that gives us our linear approximation. Okay, here I have put these quotation marks because this is not generally defined what is the derivative with respect to an entity that is a graph, right? But for example, you can imagine that if we have, say, a fixed topology and what we are considering is only the states associated with each node of the state graph. So basically this becomes a gradient with respect to a vector of dimension, the number of nodes, okay? So in this case, depending on the specific implementation of the predictive model, this could be defined in different manners, okay? So we can think of it at this point as the derivative with respect to the node signals, okay? So taking this derivative results in a matrix H of t, which basically defines our linear readout over here. The noise is no more the exact same noise, but it is affected by these other terms here. So we have a different noise that can have a different covariance matrix, for example, but still it's a noise that we can deal with, okay? So this is the principle of the linearization of this entity. So it's important to understand that this depends on time, okay? Depends on time, potentially depends on the topology of the graphs involved, and so on. And so this is not a global approximation of our nonlinear readout. It's just an approximation around the current condition that we have, and we expect that our system has learned already how to estimate the system state good enough so that our approximation our refinement doesn't need to go very far away, so that, and the less far away we go, the more precise this approximation is, okay? It is known that extended Kalman filter has some drawbacks in this respect, depending on the level of nonlinearity of our system, but it's a first example how to approach this problem. There are other methods as well, of course, that could be possibly employed. Okay, and so as this changes at every time step, because we change our states, it's unfeasible for us to define by hand what is the derivative at every time steps. And in fact, what we can do is rely on automatic differentiation libraries that allows us to operate very neatly, at least from the designer perspective. Of course, we need to operate with all these entities, take the gradients, and also invert to compute the Kalman filter. So this, of course, entails some overhead in the computation, in the time complexity, but still it is doable without any to bother too much on making the computation by hand. Okay. So overall, the algorithm for the graph Kalman filters operates as follows. So at first, we have our model f theta and fc, which is not trained, so we need to train it. And to train, what we can do is simply train our not stochastic, but spatiotemporal graph neural network as we do usually, for example, using stochastic gradient descent, optimize our parameters, possibly without using the Kalman refinement, and then at the moment that we reach the best parameters, we pass to the testing where we may employ the Kalman refinement. So the inference step that we carry out during training is as usual. So we take the last estimate of the state, the system state. We make our transition to H, and then from this new state, we make our prediction. Okay, so here, if we're not using Kalman, these two steps, these two entities are the same, okay, because there is no refinement. But when we move to testing, after having carried out these steps here, at a certain point we may observe the y, so the true y. So we compute all these Jacobians that we can do, for example, with automatic differentiation. Then we compute the Kalman gain, which is a function of these plus other matrices like this. And we refine our states according to this linear rule here, okay? And then by this, once we have this, we fed directly into this before taking the next state transition, okay? And repeat again. So what I've said, anticipated actually, is that not only we have an estimate of the current states, but we also have an estimate of this error here, okay? This is really important because it allows us also to make our prediction probabilistic. We don't need necessarily to tell only for example, the best point-wise prediction, but we make also prediction based on the variance of our estimates. And here we have also the noise, right? A few slides ago, I show you that the Kalman also depends on the readout noise. And this noise covariance either need to be known or to be estimated, okay? If we need to estimate it, we may require to have a probabilistic model that is involved in here, so that we pass at every iteration while learning that our parameters, also some samples drawn from this probability distribution that we are currently learning. Otherwise, what is typically done is that these components here are removed. Okay, so this is basically it for what I wanted to discuss here about the Kalman filter, and I want to present you some empirical results on controlled environments that allows us to really pinpoint what are the main elements involved in the process. Okay, do you have questions so far? Okay, otherwise I'll move on. So we are going to consider these two data sets we call lean and non-lean graph state space data sets. As you can imagine, one is going to be linear and the other non-linear. And both of them are created as follows. So we consider this graph topology associated with the states. So we are removing at this point the part of graph learning, because as I showed you here, basically we can carry out the process all before the Kalman filter. So I assume that we have already learned that from the given data. And to each of these nodes, I fed, or I generated input signals. And these input signals are done like so. So basically are random binary signals, which stays around 0 for a certain amount of time, then go up to 1. So as to roughly, you can think of it as a charging each node signals for a certain amount of time, and then allow the system to either discharge or dissolve or whatever. Then we have the states. So these, of course, are only the states signals, so the node signal associated with the states, still regarding these two here, and we see that there is some fluctuation, that these nodes interact among each other according to these rules. So we have a message passing that operates after having combined the input signal, so this S of X denotes the signal associated with the input graph with the signal associated with the state graph. After having combined in this simple way, we perform some message passing and then add some additive noise. Okay, so this is why you see so noisy curves, but you can see that there is some relations, very mild actually from here. Maybe it's a bit too far-fetched to understand, but if you look better at the system, the real data, you see that basically this square curve basically is charging the signal of the states and then allow some time to let it discharge, depending also on the neighboring nodes and the associated signals. Okay, and then we have a readout, and the readout is simply applied node-wise. So for each node, we apply the same function as a readout. So here it's you can see that it's pretty much related, and it is sort of capped between 1 and -1, because this is the nonlinear version of the data set. And the distinction between the two is that we use or not use nonlinearities at the state transition level and within the readout function. Okay, why I decided to use linear and non-linear data sets? Well, because for a linear system, we exactly know what should be the optimal one with respect to the mean squared error. Whereas for the non-linear, it is not possible in general and depends on several entities that create a bit complication to really pinpoint if we are doing everything appropriately or not. So let's start from the linear data set. Okay, here we have the prediction error. So basically the mean squared error computed without the Kalman filter and with the Kalman filter. Okay, this model here, you can think of it as it is trained. Actually, it's not trained because it's set exactly to the system model. So it's you can think of it as the optimal model. But even you see that the optimal model that has the parameters exactly set to those that generated the data results in a mean squared error, which is of this magnitude, and it's larger than the error that we would have if we were to use the Kalman filter refinement. Okay, this improvement here is expected even though this is a system model. Why? Because this part here is affected by, so it's continuing making a prediction about the system states, but cannot take into account the random perturbance brought by the noise terms. Okay, so at a certain points, all these errors piled up and roughly keep the states estimate less accurate. Whereas by the Kalman filter, what we have is that at every step, we can make this refinement, okay? And this refinement keeps us on track better than without it. And what I stress here is that this is not the prediction after the refinement. So we observe the target, refine the state, and make again the prediction. This is only carrying out the refinement from previous states only, okay? So basically this refines until step t-1, but the prediction at times t is made only based on the a priori state estimates, okay? This is important. Then we have these two baselines where instead of carrying on or piling up all the noise, the error associated with the noise and the states, what we do is that we set every time the state estimate to the expected state. Okay, this is basically, again, reproducing the optimal mean square error predictor without knowing the exact realization of the noise at that time step. Okay, and we see that here the performance are the following, so are roughly the same of these, of the previous one with the Kalman filter, which is trying to correct because of the noise that we, the error that we continue accumulating. And what's important to notice is that it doesn't change the performance before and after using it. Okay, why? So because this is already optimal, so we can try to make some improvements, but overall this doesn't bring any substantial improvement on the long term. Okay, because all the improvements that we can make because of the Kalman filter may be noises as well because of the noise associated with the target. Okay, whereas this is here only just for baselines, and is what if we knew the exact noise that we had at that moment, so we have the true state, then the prediction error is only associated with the noise of the readout. But this is, of course, even farther away from what we can get in any real scenario. It's just to see it as a baseline. Okay. So then we trained two models, these two STGNN. We have the first one and the second one that differs on this element here, whether the system model, so the model that generated the data, is included in the family of predictive models that we can that we consider. Okay, so basically, if training these models, the parameters of this model, I can reach this system model, or I can only approximate it. Okay, so STGNN1 contains this. STGNN2 does not contain the model, so I can only get so close, but not exactly to the system model. And in fact, what I see is that STGNN matches the performance of the system model. It's pretty simple, and we saw also by looking at the parameters that it has learned that it reaches that point. Whereas this other model here, it gets close enough, we may say, but it's not as good as that. And this discrepancy or this misconfiguration of the model does not allow us to improve that much as in the first case, but still it brings the mean square error farther down with respect not using it. Okay, so this is still a reason why when possible using this refinement it's appropriate. Okay, how am I doing with time? 45 minutes, right? So
so we're close to the end, or at the end-ish.
okay. So I will conclude really soon. So I have this other index here, which I called relative prediction improvement, which is basically comparing the prediction error here after the refinement and before the refinement. Okay, so are defined here. This is before the refinement, where I have not refined the state, and here once I have refined the state. This is not a real case scenario, so I cannot, well, I can make prediction like so, but in such a case, in such a scenarios, I already have the true output, so there is no reason to consider this. But this allows us to understand what the Kalman filter is doing. So the Kalman filter here is trying to improve this quantity here to match the actual observed system output. Okay, and we see that basically the very bottom of this, so the best possible value of this RPI is basically minus 100%. When this it occurs when this is 0, and this of course are equal, so this is roughly what we get in all these scenarios, except for the last one. So in these scenarios, which are well fitted, it is able to improve really close to bringing this error here almost to 0, except in this case where we have some misfit of the model to the system model. Okay, but still, this is an improvement that we can obtain, which is larger or lower than 0. So it's an actual improvement. Okay, so we also have the results for the linear system. The only thing that we need to understand is that for what concerns this first part here, we have very similar behavior than we had with the linear system. The values changes because the system changes, has changed at least. And what we have instead regarding the STGNNs is that the train model, this one, achieved better, both actually achieved better performance than the system model. How so? Well, because this is a nonlinear system. As I said, the predicting only based on that may not yield the best mean square error performance, because the nonlinear system involves the noise that passes through some nonlinearities and so changes the expectations and so on and so forth. What we see is that moving from the left column to the right column, we see improvements overall, except for this, because we said which is the baseline. But from here to here, we see a greater improvement with respect to the top part. Okay, this is because the model is capable of learning a better model that brings some improvements with respect to the system model. Okay, and similar from here, we see that in all scenarios, basically the Kalman filter refinement brought some improvement. And so I guess this is it. And I'm here to answer any question that you may have. And thank you for having listened to me.
Thank you very much for your talk. It was very interesting. Does anybody have any questions or still have time for questions?
Yes, I have some questions. If you can go back to the slide where you do the Taylor expansion, the matrix that you have to compute the derivatives, this h of t. You said that is the derivative of the graph signal, but with respect to what exactly? To time or
no,
to itself?
the derivative. So take this function here that you should be able to encounter, right?
Okay, it's a derivative of that function with respect to...
Exactly, the derivative of this with respect to the first variable, and the second part with respect to the second variable. If it were vector, this is a standard gradient with respect to h and with respect to no.
And you have to compute this at inference time?
Yes.
Okay, so this can be maybe a drawback compared, or at least the overhead is the main overhead, which is...
Yes, correct.
Okay, and you have an idea how this could actually scale compared to, I don't know, training time? It's comparable to training time, or do some epoch when you train or something like that?
Well, that depends on how good you are implementing also things. To be honest, I cannot tell really at the lowest level how quick you can get over here. My feeling on my implementation, which I don't say it's really well implemented, my feeling is that this can explode if you are not careful enough when defining these gradients. For example, in defining the operation to compute these gradients. For example, here, or at least in the experiments that I did, this readout was the same for all nodes. And so basically the same function applied to all nodes. If I treat this function as a multivariate function, then when computed the gradients have accumulating so many intermediate gradients, so quantities, and also many of them are 0. So if I can exploit such a structure and define in an appropriate way, what I can get is that both here And also regarding the state transitions that also combines nodes, different nodes, I can leverage some structure in my data. For example, some stationarity in space, okay? This can further bring down. At the current moment, the implementation that I have, you can feel that it's getting slower, substantially slower than when you have just inference. I don't know if it is also related to, that, for example, I'm using PyTorch. In PyTorch, you have this inference mode that allows you to even speed up the testing phase by disabling and not creating some hidden stuff. I don't know how to describe it. And by disabling that already, you can see some slowdown. So this, of course, it's a drawback, and scales with the nodes. And another element that impact the efficiency of the method, it's associated with that. No, where is it? Here. So the Kalman gain, it entails an inverse. So this inverse, most of the several times, it's not that complicated to compute. For example, H in our case become diagonal. So all these operations become easy, especially if you have this part here that has some noise, and the noise is substantially is not zero. This inverse here brings up to a not so bad condition problem. So it's not that complicated to compute. Actually, you don't need necessarily to obtain the very optimal Kalman gain, because this is the best you can do, but you can go close enough and still obtain some satisfactory performance. So I don't know if I answered your question. I just played around with that.
Yeah, absolutely. Yeah, thanks. Thanks.
I have one more question on the experiment part. For the refinement, you do this refinement step after every prediction step, right?
Mm-hmm. Except, so if you have, let's say that you are training manually in some sense, you have your batch, you have your time window, you iterate from each time step of the of your batch. Of course, you don't see the target that you want to predict. You only see the output, which are somehow the target, but from the previous state, from the previous time steps. So I use all of this, but except for the last one.
And do I understand correctly that without the Kalman filter, it gets harder and harder for the model to predict, right? Because it doesn't get any updates over time. How many time steps do you have in your data set for the experiments?
Oh, in this case, I have, I think, 12, but for these simple models, fewer could be enough. So deciding it is an hyperparameter. Unfortunately, you know that if the system is stable, after a certain point, the initial condition that needs to be set somehow, so the impact of the initial condition vanishes, and what you have is just the best estimate that you can have, even for longer time sequences. So in my experiment, I just made sure that I was a sufficiently large sequence.
Okay. And the noise in the experiment is known?
The noise in the experiment, no, we have noise at the state transition level and at the readout level.
Yeah.
It's known. Yeah, yes, it's known.
Yeah, okay.
I heard it's none. Sorry.
Yeah, okay.
Yes. This is the noise you can also learn if you want. The only difference is that throughout the training you need to account for that, and learning also the level of the noise that I was mentioning.
Do you have some rough estimate of how much worse Funks would get if you would have to learn the noise? Depends, I guess, on the noise.
depends on how good your model is, or your training procedure is in learning the model. So it depends a lot on that. So if you are really good on that, you should basically meet the same performance. If not, you have some misclassification. I don't have examples here, but for example, in this case, I have some other parameters that are slightly misconfigured. So you see that the MSC in the standard setting has this discrepancy over here, 0.005. Okay, and already in the Kalman refinement, we see a substantially larger difference in performance. Okay, so this, of course, everything relies on the fact that we have a sufficiently good model. How sufficiently good? I don't know how to answer actually this question for two reasons. One is associated with this misconfiguration. The other is associated with the approximation of the system with a linear, by means of the linearization. Regarding the nonlinear aspects, there are methods to improve over that. For example, you may have heard of the unscented Kalman filter. It's basically using other techniques to approximate the system.
Okay, thanks for explaining.
I have a question. Basically, I try to remember what they learned about in the university, about the Kalman filter. You usually use Kalman filter when you do know that transition matrix and the output matrix, but you cannot access to the state, right? Here, you're saying that if you don't know it, you can learn it, right? You can learn not necessarily the matrices, but also the function, by the data, and then still apply the Kalman filter to assimilate the output to fix the state, to estimate the state. But if I recall correctly, there were other filters back then that we used when we do not know the state of the, we don't know the model itself. We don't know the transition and output matrix. It's something like the particle filters or stuff like that I'm trying to recall, but there were some, other type of filters, not Kalman one, that were used to be used where you don't know actually the transition and the output functions that you can use to try to estimate them. I don't know if you have tried to apply those techniques, since we have some kind of uncertainty, right? Because we are trying to learn those matrices or those functions. We don't know necessarily the true value of them in general, right?
Yes. So the particle filtering that you were mentioning is actually also the I think at the core of the unscented Kalman filter, which is it's called Kalman filter. Also, the extended Kalman filter has this Kalman part because it relies on the developments of the Kalman filter under the condition that you've mentioned, where you know the system model, basically almost everything except for the states. But none of them rely necessarily on further knowledge. The particle filter technique is developed actually for dealing with nonlinear systems that can go more nonlinear in some sense than what the extended Kalman filter can, which relies on this Taylor expansion. I didn't try explicitly them. The difference between all these other, let's say, variation of the Kalman filter and also other filters, for example, you may imagine, I don't know, or recall the recursive least squares. It's another filter that tries to optimize in some way the states or the weights, depending on how you cast the problem over time. And the point is that all these methods depends, in my opinion, so much on the problem setting that you are considering. So this, at least for this paper, we didn't have in mind to compare all of them. We just took this Kalman filter that has very nice properties and guarantees, at least in the linear case, of course. So this is the reason why we consider only this. But of course, also other extensions are possible.
Great, thank you.
Welcome.
All right, I think if there are no more questions, I would say thank you very much. And
Thank you. Thank you for having
that's
me.
it. Thanks.
Thank you very much.
Thank you.
Bye.